Okay, so we're very lucky to have Dr. Nigel Goddard here with us today, one of the first kind of international speakers we've had in a long time.
In person, anyway.
Yes, that's right. Yeah, so Nigel is a reader at the School of Informatics at the University of Edinburgh in Scotland, and it looks like he does a lot of work at the juncture of computer science and energy, and has been involved in a bunch of projects across the UK and European Union. So they look all very interesting, and we really look forward to hearing about what you've been doing, your group's been doing. And so I'll pass over to you.
Yeah, so I'll just give you a very little bit of background on me and how I got to what I'm working on. So I started out my PhD work in artificial intelligence, and I got really interested in how the brain worked. And I spent 20 years or something working on how the brain worked. And then I had an epiphany and realized that the brain is, well, it's a fascinating problem. It's not actually critical, whereas climate change is critical. And so I started looking at, what can I do with respect to that, and looked around. Eventually ended up with energy. And my sort of technical work in computer science, I'm very interested in machine learning methods. And so I basically do applications of machine learning in the energy space. And in the course of that, I've become more interested in things like human-computer interaction, and you'll see why that's the case. So what I'm going to do is do a quick tour through quite a lot of different projects. I'm not going to go into a lot of depth in any one of them. There'll be a few places where there's a bit more detail, but I can talk in more detail about almost any of them. So let's see now, how are we controlling this?
Probably from your laptop.
Yeah, that's what it should be.
Once more.
Okay, I'm just going to scroll. Hang on a minute. This will probably do it. Yeah, okay. So, all right, so I'm going to talk about essentially 3.5 different areas. So most of it will be about the domestic energy work that we've done over the last 8 or so years. Which is under the rubric of the IDEAL project. I'll talk a little bit about our work in non-domestic energy, and then I'll get on to how this is all starting to move into health-related and particularly social care-related areas. And then I'll spend a couple of minutes on what we're looking at doing in the future. So the IDEAL project ran from about 2013 to 2019. And I'll tell you about what we're trying to do, and then how far we got along with that. We certainly didn't achieve everything that we were hoping to do in the project. And I'll focus a little bit on disaggregation, which is non-intrusive load monitoring. So some of you will probably know what that is, and some heating studies that we've done. So the idea with the IDEAL project was that we would censor up a whole lot of dwellings, and we would then take the sensor data that we were getting streamed and clean it up and do various kinds of inference on it to figure out essentially what are people doing in their homes that uses energy. And then we would generate feedback and advice to people automatically using these inferences, and then give that to them through a user interface that we designed. And the idea was that would affect their behavior, and then we would be able to detect there's been an effect on their behavior because we have all these sensors in the house. So we have this loop. And that was the grand idea. We did the censoring bit, we collected the data, we did a certain amount to do with inference, and a little bit to do with feedback generation. And we have collected a lot of data. which is most of which is just being released. And it certainly has had some effect on some people's behavior, but we haven't done the analysis on that yet. So I can't really tell you anything about how that feedback worked, but there was a lot of interesting stuff along the way. So the motivations for this, like a lot of countries, the UK is engaged in rolling out smart meters. And there's this idea that all that data that's coming through from the smart meters, you might be able to do some interesting things. And in the UK, I don't know how it is here, but smart meters come with an in-home display. That is, the idea is that it's going to help people to reduce their energy use. So the kind of rationale for why it was worth investing all this money in smart meters is it's going to make energy use more, reduce energy use, and that's good for society. I mean, actually in practice, the smart meter program is substantially motivated by things like wanting to automate billing and being able to disconnect people without having to go into their homes, which you have to obtain permission for. So, not these energy-related issues. And the idea is that was that we would look at how we could engage homeowners in understanding their energy use and potentially modify it. So we built the sensor system. We have these little sensor boxes, which could measure electric current at 1 second intervals. In the UK, a lot of houses are heated most houses are heated by gas. So in fact, all of the houses in this study have what are called Combi Boilers in the UK. So those are instant gas water heaters. And the water it's combi because it heats water for space heating with water radiators and water for domestic use like showers and baths. So here's one of these sensor boxes attached to this radiator, and it's got temperature probes on the inlet and the outlet. So we're gathering this data. So we could gather gas pulses, and that's not on a second-by-second basis, but a certain amount of gas. So when there's a lot of gas being used, you're getting a lot of pulses. And when there's a small amount, they can be half an hour apart or more. These sensor boxes recorded ambient temperature, ambient humidity, and light level. We really just put the light level in because we could. We weren't really sure what we'd do with it. But temperature and humidity are clearly energy related. And we also set it up so we could plug in these temperature probes for measuring the temperature of key hot water pipes and things like cookers and so on. And the whole system was set up with a Pi base station to gather the data from these. So this is the Pi. These are the areas that increase the signal. And that's connected to people's home routers. And we designed it to have a 3-year battery life so that we didn't have to go back the idea was we wouldn't have to go back during the life of the project to change the batteries. And this system is still far ahead of anything I've seen in the market, particularly still with battery life. And it's pretty much because we have a very good group at Informatics Edinburgh on low power networks, and we had one of the postdocs there design this system. So we built about 6,000, had about 6,000 of these sensor boxes built, and a whole program of installation in houses. I'll go through that in a minute. So we did in household recruitment. We recruited close to 300 homes to the study. So 250 or so were kind of in the standard category, and we offered to suitable ones to get more detailed monitoring. So the standard installs had what I just went through: electricity, gas, combi boiler, and ambient room data for pretty much every room. The enhanced ones also had a lot more data. So every radiator was monitored, cooking device temperatures were monitored, and individual electrical appliances that use quite a bit of energy were also monitored with a separate system for that. The installer did a survey of the property, so noted room sizes, took photos and so on, and had the participant do a survey to do with their demographics, how many people live in the home, what their ages, income and so on, and attitudes to things like energy and the environment. And this survey was done for 6 months ago. So this is the kind of data that's in the data set that is being released now. And for feedback, we developed a tablet-based, we developed a website and embedded it in a tablet-based app, and we gave every participant a tablet. And the standard smart meter kind of view that we showed people, so we divided the participants into ones who would get standard views like you would get with a normal smart meter in-home display, and then ones who would get more informative ones. And this was to look at, does more information or better information or tips or hints or games or whatever you want to try, do these things have an effect over just whatever the standard smart meter is? And I like to think of it as we were trying to actually put the smart in smart meters, because smart meter displays don't really actually, there's nothing very smart about them whatsoever. So we showed them the standard kind of dashboard where you have electricity and gas, and you can get various simple kinds of charts. Some of those slides going off the screen, but we had some more advanced views. So you probably can't read this, but here there's a list of rooms and the temperatures. So that's not something you get from a standard smart meter, but we could do that. We could do comparisons of different rooms and what their temperatures are, so temperatures and humidities. So we did some experiment with that. Now the foundations of this kind of feedback that we looked at, the project had sociologists as key members of the project team, particularly Heather Lavelle and Jan Webb. And they brought to the team this the sociologist notion of practices in the home, which you may be familiar with, but basically the idea, to put it in a more sort of engineering speak, is that people develop habits or practices around energy use. And it's not so much energy use, but things that you do in your home become habits, and they may or may not involve energy. But if you want to actually change what people do, you have to change habits, and that's a lot more difficult than just giving people someone a piece of information. So we thought of feedback as a conversation about habits, and that's how we we tried to couch it. And you can, as an example of this, of these kind of practices and what's considered normal and what people are happy with. When I was a teenager in England, we had, in terms of cleanliness and washing, it was perfectly normal to have a bath twice a week, or maybe once a week even. And that was that was fine. If I was to tell my teenage kids when they were teenagers that that's what you're going to do, they would go, ugh, right? They would say, no, I have to have a shower every day. And these are the kind of practices that they're not an individual thing, they're a social thing. So changing them is not a matter of just persuading one person this is what you should do, all their friends and so on. So it's it needs to be thought of as a socio-technical system. We also tried to involve the householders in the design of the system and the feedback. so that we're focusing on questions and problems and that the users have. And we tried to use co-design methods to do that. So I'll go through a little example of this. So if you think about practices, we might talk about something like cooking or cleanliness or something like this, but actually these involve lots of individual steps. They need to be broken down. And if we think about laundry, the sub-practices involved in laundry are things like how many times do you wear a piece of clothing before you consider it needs to get washed? So that's a practice. How do you actually wash it? Do you wash it by hand? Do you wash it in cold water? Do you wash it in hot water? What's your practice? How do you dry? Do you hang it up to dry? Do you tumble dry? Do you iron? If you iron, how are you doing that? And if you're not ironing, if you've got some way of getting creases out of things. So this is something that, for some people this matters a lot, and for some people it doesn't matter at all. And of course, these things aren't independent, completely independent in practice. So to engage with this, what people do in their homes, you have to get down to this kind of level of detail. In terms of what we might think we could do, the kind of things that we'd like to be able to infer based on that sort of breakdown is like how many times are people wearing clothes before they're washing it? Not much chance of doing that. The washing temperature. Well, if we know what the washing machine is doing, how much energy it's using, maybe we can do something with that. Spin speed, which is a drying activity. Can we figure out whether it's on a high spin speed or low spin speed? We can advise people on the effect of that. Drying methods and decreasing and so on. So this isn't appliance use per se, right? So this isn't are you using the washing machine or not. It's how you're using the washing machine. And if we want to provide this kind of advice and interaction with homeowners on this, then you need to get down to this kind of level of detail. So as an example, this is all a bit. Let's see if I can. Not sure if I can make this smaller. Hang on, let's do that. Yeah, that's a bit better. Okay. So if we look at this is the electricity signal. So how much electricity is being used in watts by time. And this is for a washing machine. We're not getting the full detail down here, but so this is what, the data that comes out. What does it all mean? So it turns out that, so this was a washing machine run multiple times. This is a 30 degrees centigrade cycle. This is a 60 degree centigrade cycle. So you can see the heater is on for longer. This is with it empty. So still a high temperature, but nothing in it. This is just a spin. So this is just a spin cycle, so no heating cycle at all. And this is just a rinse. Not quite sure why there's any heating on there, but maybe it was a slightly warm rinse. And in terms of spin speed, these, if you focus down at the end of so this, for a washing machine, this is a heating cycle here. This is the kind of washing here, and then this is the spin. So it doesn't take much energy to tumble the drum, but it takes a lot more to spin at a reasonably high speed. So spin speeds, this is a low speed spin and a high speed spin. So these are the kinds of things that you look at it and I think, okay, if we could get training data for this, if we could get labels, if we get somebody to tell, look at these and tell us what's going on, then we might be able to use a machine learning algorithm to learn to pull these things out of what's happening in the home. but you know, there's no well, some washing machines probably have interfaces where you can pull that data out, but very few of them. You know, what's going on in the washing machine. So we looked at how do we get the users to give us this training data. So we started looking at user interface design with the homeowners to see what sort of interfaces they would like that would give it, and also that would give us the kind of information that we wanted for these training purposes. So we used the co-design method, and we used the enhanced households as the cohort for doing this kind of user interface design. So I'm not going to go into more detail about that, but basically, in terms of feedback, it was organized around practices. It was about enabling users to do something, and we used these co-design methods. So my conclusion from a lot of this work and interacting with a lot of homeowners over time about these things was that the sort of my engineering bias to let's try and automate things is not going to work. And what you need is, or the best we can hope for in terms of these kind of methods is to have user-centered automation. So you find that technical improvements are often not used properly by people. So, I mean, classic examples are, you know, programmable thermostats for your home that will, you can say, you know, come on in the morning, come on in the evening. Too complicated for a lot of people. They just use them as on-off switches. So what's wrong with that? Well, it's probably the user interface wasn't designed well. Another thing is that is talking about changing practices, behavior change is really difficult. So the kind of direction that I would like to go in with this is think about automated energy management systems where there are interfaces that let people easily modify what the automated system is going to do. And when people do something different than the automated system thought was the right thing to do, the system learns from that. And you know, it's a very general concept. And you can think of, I mean, a lot of systems we have in our homes are pretty automated. Look at a fridge. You don't turn the compressor on and off, right? But you have got a control to say how cold you want it. So this is the sort of thing that we might need. So for example, with a washing machine, you could think of it having a much easier, a user interface that, you know, people could give input as to when it was doing the right thing. It could suggest, I think this is the kind of cycle you want to use, and you could adjust it. So in terms of, we're focusing on building and, you know, energy use in building. So the idea on building, so the idea is that the building automatically does things, and when it doesn't do the right thing, then you can tell it what you want it to do, and it learns over time. So I think the future of these kinds of things is to think of them as assistive technologies for people. And in the UK, well, this is going off the screen, but I don't know if are electric vehicles being adopted here in New Zealand? Yeah. So electric vehicles, and people are starting to adopt heat pumps in quite a big way. Those are two massive power draws when lots of people are doing it, that there's no way we can let people just do it whenever they want. So we're going to need to have automated systems, but people are going to need to be able to say, I don't want to do it what your automated system wants, I need to do something else because today is different than the usual one. Okay, so let me go on and talk a little bit about non-intrusive load monitoring. So this is some of the machine learning work we did. For anybody who doesn't know, the non-intrusive load monitoring problem is if you're recording the electricity signal at the meter for the whole house, can you figure out which appliances are on when and how much energy are they using? So we initially started out using hidden Markov-based approaches, and the problem with the hidden Markov approach is that the problem is essentially under constraint. So there aren't enough, if you just say at every time point, the appliance power draws have to add up to the total mains signal, it turns out that there's not enough, that's not enough of a constraint for you to uniquely find a solution and find the power draws. And the kinds of things that people have done in the hidden Markov model world to get around the fact this is an under constraint problem is to add more constraints. So one of the advances that was made in this area some time ago was to say we're going to add the constraint that only one appliance can change its state at any one time point, with the idea that you're probably not going to turn the washing machine and the kettle on at exactly the same time. That's maybe less real now that we have things that are on timers, electronic timers. But at the time, that helped quite a bit. We did some work to add the constraints that, we know that although a kettle uses quite a lot of energy, it doesn't use very much energy over the day on the whole, because you don't use the kettle that many times. So we added constraints around the amount of energy that an appliance could use over a particular time period, like a day or a week. Anyway, that all got taken over by deep neural networks, like most things these days. So yeah, Jack Kelly, I think at Imperial was the first person to apply deep neural networks to this problem and showed that it worked pretty well. So he used an approach called sequence to sequence, where you take a time period of the input signal, so the main signal, like maybe you take an hour of it, and you try to predict for each appliance what's its power draw during that time window of an hour. And we made modifications to this to, instead of using the time window to predict the 60-minute time window to predict the whole 60-minute output, we would just predict the central time in the middle of that window. The problem with sequence to sequence is that or one problem with it is that you're predicting, as you move your time window along, you're making multiple predictions for every time point. And so what do you do with that? Well, what Jack Kelly did was to average them, which is a sensible thing to do. But when you get to the edge of the window or an edge of activation, it's not particularly good. So it turned out the sequence to point worked significantly better. And then we did some work on using, for anybody who does deep neural networks, dilated convolutional networks, which are somewhat modeled on the human visual system, and they are massively more efficient and work almost as well. So I'll show you a few results on that, and then we also did a study of sampling intervals. So the standards, we were recording data at 1 second intervals from the mains and from the appliances. In the UK, the smart meter standard is that it reports 30-minute data for billing, and it reports 10-second data for third-party applications in the in-home display. So we did a study of this, well, how does it affect your ability to actually do this, perform this NILM, whether you have 1 second, 10 second, 30 minute. Let me put this. Okay, so the fully convolutional, dilated fully convolutional neural network, for anybody who does this, the idea with dilation is that each layer you increase the receptive field size. So in the case of an image and your visual system, the receptive field is for any in the brain or in a neural network its artificial neurons, how much of the image is it looking at? And in the human brain, if you're at the retina, it's tiny, tiny little things. You can see very high precision. When you get high up in the visual system, you have neurons that they are looking at the whole, everything coming in through an eye. And this kind of dilation allows you to get this spatial increase.
Can I just ask some clarification? So with your skipping input locations, you literally mean that you don't use aggregates.
Yes, that's right. That's the way.
That's what I'm not complaining. I'm just asking. Yeah,
no, that is, and that's the way. Quite a lot of people have used it. This isn't an invention of ours. It's quite a lot of people use dilated networks, and that's the standard way to do things. It's not actually the way the visual system works. The visual system aggregates. So I'm kind of interested in exploring that. So in the case of what we were looking at, we're not looking at images, we're looking at time series, and we're looking for a pattern in the time series, which is like a pattern in an image, except we've got one dimension, which is time, whereas an image has two dimensions. So what this allowed us to do is to have the network look at up to this is 4.5 hours of input. And you need something like that because washing machines can take 3 hours to do their thing. So if you have less than that, it's not going to work. So this worked well, and this is an example of the sort of the predictions. So up here we've got in blue the ground truth for an appliance. Electric kettle, microwave, washing machine, and in green, what the mains recording was. Now, you might think, okay, why is the mains less than the kettle? And it's because we were recording the mains, we were recording apparent power, we just had a current cloud. Whereas for the appliances, we were recording real power. So there was a discrepancy in what's being recorded. And that's one of the things you have to cope with when you do this kind of work in practice, because getting real power at the mains means you've got to be measuring voltage, and it's much more complicated. But you can see here that the fully connected network is getting better fit visually than the standard sequence to point network, which didn't have this kind of dilation. So let me show you the results in terms of performance. So the two measures we used were mean absolute error and signal aggregate error. So mean absolute error tells you, kind of on average, how badly wrong are you. And signal aggregate error tells you over some time period, you add up it all, how badly wrong you were. And you can see that going to the fully convolutional network hasn't really changed the performance dramatically compared to the sequence to point networks. It's better in most cases, but not dramatically so. But in terms of the training time, it's a massive improvement, 2 orders of magnitude. And that matters if you're trying to build a production system that's actually going to support, thousands or hundreds of thousands of households. And even for 250 that we were supporting, that mattered. And so the fully convolutional dilated network was good enough for our production system. Okay, I'll go through this really quickly. So we looked at sampling intervals for norm and how well that changes. So we're basically looking at 1, 2, 4, 8, 10, and so on, up to 30-minute sampling intervals. And this is what it looks like. So you can see, so this is the F1 score. So this is a measure of kind of how accurate are we at determining when the appliances were on or not. So this is a measure of whether them being on or not. It's not a measure of power use. And you can see that as you would expect, as the sampling interval becomes bigger, you're getting less information and you're going to do worse. So the F1 scores, a value of 1 is fantastic. That's good as you can get. Values down here are really not good at all. And you can see that the 10-second UK standard is, kind of significantly worse than if we had, say, 4 seconds. At the time they set the standard, they didn't actually, the only reason they set it at 10 was because they didn't have any good data as to whether it should be 1 second or 100 seconds. And so somebody just picked a round number. But this suggests that it would have been better to have picked a smaller number, at least for these purposes. And this is a kind of signal aggregate error normalized. So this is something where you want to be low. And again, this is the 10-second, and this is the 30-minute. So you really, 30-minute data is basically pretty useless for doing any kind of disaggregation except possibly electric showers. Okay. So we did some work on whether we could infer whether heating was on from the room temperature and humidity measurements. So we used the room temperature and humidity measurements. We also gave the network the external temperature and humidity measurements because that's going to have an effect. If it's very hot outside, then it might be hot inside with no heating. So we found that we could predict just from temperature and humidity, we could predict fairly accurately when radiators were on, if they were on for a significant period of time, like more than an hour, but less than that, the network tended to find it. I'll move on from this. So yeah, you can see that the precision and recall in terms of predicting these radiators being on or not was pretty good in general. And in terms of durations that were on for, this is the ground truth, so the neural network model kind of underestimated sort of low duration and higher duration somewhat, but much better than any kind of simple baselines that we could come up with. So that was interesting. It was something that we didn't know before we did this, that we'd be able to do. It's not at all obvious that you could tell whether radiators are on just from temperature and humidity. Okay, so I'll just move on to work on non-domestic buildings. So we did some work with public sector organizations, the City of Edinburgh and the University of Edinburgh, on energy use in some of their buildings. And it's a completely different problem than households. So they were, these organizations are fairly large. They've got emissions, goals, and they want to reduce spend and so on. So they're quite interested in energy use. And then we selected, with each of them, we went through a process of selecting buildings that they thought were valuable, that there was some building information available, some sort of system. There were people who were willing to engage, which is critical. And in particular, where the opportunities for energy saving are not, put in a new system, but how can we change behavior? So there are some places where, just putting in a new system is the first thing you should do. And there are other places where it's all working fine, but people aren't using it properly or could do better. So that's what we were looking at. So we worked with, went through a long process of, and Jan Webb was involved in this. She works on sociology of organizations, so it was really helpful. So we worked with senior management and energy champions to select these buildings and then engaged with staff. And we used an iterative co-creation process where we worked with the staff to, first of all, try and let them come up with ideas about, like where are the problems? So what's the problem in this particular organization? Then how can we come up with ideas about what to do about it? And then what sort of innovative computational based things could we do to give the opportunity to save energy? So I'll just really go through really quickly a couple of these. So at the University of Edinburgh, we worked with the Rosalind Institute. The buildings people had identified labs as a place where a lot of energy is used, and could we do something about that? So we went through this co-design process with people at multiple levels in Roslyn and built a little device for interacting with lab equipment. And it has a little interface. So this is the size of it. You can see here's a card, ID card, and a little interface that put up these kinds of screens. So it tried to encourage people to share equipment use. So in the labs they were looking at, they had heating baths that would heat up various kinds of reactions they were doing. And you could sort of fit more than one experiment in the same bath, but they often didn't. So it suggested, if you just change the time that you're going to do it, maybe you can piggyback on someone else's. So we installed a number of these devices in 2 different labs, attached them to the wall, connected them up to the. This is an incubator. And these are the kind of interfaces that people have to deal with it. So, this is another thing. Yeah, exactly. So this is, it makes a difference in the amount of energy used. So these are the results that we got in a sort of, I forget how many months it was that it was installed. It's probably only about 4 or 5 months, something like that. But we had 70 different users involved in it. They made 166 bookings through it. And the kind of end result was there was a drop in the on time of the devices that were being monitored, 20 to 25%. And that is a cost saving. This amount, which is much less than the cost of the little device we had, and this is the amount of energy saved per year. So these are sort of small numbers, but if you imagine these kinds of interventions scaled up across all the labs in a country, you could be looking at significant savings.
What's the approximate percentage of the consumption of the devices?
Yeah, I don't know. That's a good question. When we were looking at these kind of results, it was mainly about, is it cost effective to do this?
Sure.
Rather than, but
because
that is a
if it is, you do it, and then you can ask other questions.
Yeah, that's a good question. And then we worked with the City of Edinburgh Council, and they identified an event space that was using a lot of energy. It's called the Assembly Rooms in Edinburgh, and it's used in the festival and lots of other times for concerts and plays and this sort of thing. So we created a dashboard for the start, and this again was using this kind of co-creation process. We created a dashboard for staff to use to look at when energy was being used and what plans were, and we also, so this is what the kind of energy dashboard looked like. And we produced a report for people who were booking events as to how much energy their event had used. And one of the things that came out of this was that we, in this co-creation process, Linda Webb, who's a postdoc leading this, developed a game for people, and a physical game, the staff to engage in about energy use, where they went through various stages of what sort of things use energy, who's got control of those things, where could there be different interventions and so on. And it worked really well. And we have, let's see, yeah, so this is, this game, we've subsequently, the City of Edinburgh has decided that they would like to use this in other areas of their estate, particularly around energy. And Marks and Spencer's, just before the pandemic, so this hasn't gotten going, wanted to introduce it to their stores. So this is really a way of, it's an engagement game to get people involved. And we have turned it into an online thing that can be done so that you don't have to, yeah, in the pandemic era, that made a lot of sense. So that's something that's had a bit more life than just the project. So let me just go on and say a little bit about the work we're doing in care. So the project, and again, it was Linda Webb who set this up. We were looking in the ideal project at, when a different appliance is turned on and can we disaggregate that? So, and she thought, oh, in the care situation, if somebody doesn't make their cup of tea at 10 o'clock in the morning, that's often a sign there's something wrong. So if we knew when they weren't doing that, we could do something. So the idea was to develop a passive predictive alarm service that just uses technology that's already in the home and is low cost. And the idea was to leverage smart meters. So we can get the 10-second data out of the smart meter, we can do disaggregation, we can know when the kettle's on. And make this available to people who, the person might not be in care. They might, I had a situation with my mother. She was living on her own. She was fine, but getting old and frail. And my sister and I were concerned about what was going on, and we've actually installed our system so I could tell what she was doing. But it's also useful for people who are in receipt of care services. So we've done this work with a housing trust, Blackwood, that particularly focuses on older and vulnerable people. And the sort of immediate motivation in Scotland was that the current alarm systems that people have, they'll have something you hang around your neck, and press a button, and you get connected by a phone line to some service that might respond. So Scotland has decided it's going to get rid of this because there are also problems with these things. People forget they've got them around their necks, they forget how to use them. They might not actually be able to use them. So Scotland has decided it wants to go to a digital system. And this is, we thought could be part of this. So the idea here was that we would take the smart meter data, we would disaggregate it to produce, which appliances we use when, and we would interact with the carers and the clients to figure out, to ask them, what do you do? What would be indicative of a problem? Because we can't, we don't know, and people are different. So, and then we would use people who are using these physical alarms. We have the data from them from Blackwood. Blackwood is supplying the systems, and so we could use that to train probably a neural network model, but might be some other machine learning model to make these predictions about whether an alarm event has happened. So that was the idea. Unfortunately, the pandemic sort of shut a lot of this down, so we haven't been able to do as much of it as we'd like. We did find that we could predict quite a lot of the appliances well enough for people that the things they said we should be looking for. When we said, okay, there's going to be an alarm here, is that right? They said, yeah, quite mostly. But there were some appliances that people used, in particular things like TVs are really hard to, you basically can't disaggregate those, low power appliances. And so my conclusion from this was that just nil is not going to be enough. In some households it would be enough, but in others you want to put in a sensor, say on the TV, that says whether it's on. So this is ongoing work. And we've recently got a new project that's going to take this, continue this and expand it for, I think, another 3 years. So this is a heat map of when different appliances are used in a particular home. And you can see, some of them, like TV, it's kind of on quite a lot over quite a lot of periods, although there are some places where it's more likely. But there are others that are, much more localized. So, this is the kind of thing that led us to believe there might be an opportunity here. Okay, so I'll just finish up with, the next project that we've just had funded is at a different level. So this is about looking at the energy transition and what kind of pathways and scenarios make sense for the UK as a whole. And my lab's part of this is really sort of the domestic end of things. So yeah, and the other part of this that relates to this dispatch project is I had a PhD student a few years ago do his project, a PhD project, was about aggregating prosumers, so people who are, they're not just consumers of energy, they may have an electric vehicle, in which case they can, they can be producing energy for the grid through their battery, or they may have solar panels, they may have other kinds of batteries. And he was looking at, can we aggregate all the flexibility in homes to create an opportunity for a market aggregator like an energy company or whatever to make money and pass it back to consumers in the half-hour market. And he found with some reasonable assumptions that would be possible. The key thing is you need to have a way in which the homeowners can tell you what flexibility they've got. So, when you plug in your electric vehicle, if you can tell the system, okay, I need this charged by 6 a.m. I don't care when, just make sure it's charged. Then that's telling you about flexibility. Or when you put your laundry on, you could say, I need this laundry done by 6 p.m. Then that's telling flexibility. So he didn't build any interfaces for people to do that. He assumed that if there was a system for people to do that, would an automated trading system be able to take advantage of it? And the answer is it could. But I think a lot of the really interesting work is in the user interfaces for these things, and how do you, because that's what's going to get people to engage. Okay, I think that's it. Yeah, so this is a large number of people over the years have contributed to all of this. Okay.
Questions?
In that last piece of work, were you looking at the potential size of the contribution to flexibility that households could make?
Do you mean in terms of kilowatt hours?
Yeah. Was he sizing it?
Oh yes, absolutely. So I think he had sort of indicative amounts of power or energy that a particular clients might use. So a washing machine, a person says, I've got this flexibility, then how much energy is that, both in terms of power and energy.
And did he go from there to look at what value might that bring into a household? Trade it as a trading item.
Yes, yeah. But the idea, his approach was not that each household is going to be kind of independently trading, but that households could choose to sign up with an aggregator. And if they did that, then what they would pass to the aggregator was their sort of prediction of what they were going to use and when, and also an indication of what sort of flexibility they had. And the idea, the idea there was that there's obviously people wouldn't be doing this directly themselves. There'd be some agent, computational agent that was collecting their flexibility, and it would make the bids to the aggregator. But there are other approaches to this that, I mean, I'm sure you know about them, where people talk about peer-to-peer trading of these things. This wasn't peer-to-peer, it was what's the role of aggregation? There are people in the Dispatch project at Heriot Watt who are experimenting with peer-to-peer systems, real ones up in Orkney. And I think that's called the Reflex system. And they are doing peer-to-peer, usually with blockchain, although I've never managed to figure out why we need to have blockchain when we can just use a database, but anyway.
On the very first piece of work with the 300 households,
Yeah.
how did you account for any change in behaviour just from becoming a participant in that project and then identifying as being part of an energy project in your house?
Oh yeah, so we didn't. That's a problem with all this kind of work, is how do you the confounds. So what we were trying to do was to look at what's the difference that more detailed or more personalized or gamified interactions has versus just the smart meter display. So everybody got the equivalent of a smart meter display. And the reason that that's kind of the baseline is because everybody in the UK is going to get that. So that was our baseline. It wasn't do nothing. Does that make sense? Yeah.
Follow up on that residential focus study.
Mm.
I think maybe one of the contrasts between the UK and New Zealand is the housing stock. And I think you mentioned at the beginning there was a bit of a survey of what the house had.
Mm-hmm.
Did you look at the data that you were receiving and whether there was sort of some influence of the quality of the housing related to the energy studies? Because I think one of my questions would be, if we're getting metering data, yes, can we see insights about behaviours, but can we also have insights about the quality of the infrastructure, the insulation?
Yeah, we haven't looked at that. There's an absolute ton of data. There's not enough people to do all the studies we'd like to do, but that's an interesting one. I mean, there has been work on that in that area. I think UCL has done quite a bit, the Energy Institute, on either I think they did a study, or maybe it was Southampton did a study where they gave people temperature probes that they could put on their thermostat. So it was just something that you attach on the wall by your thermostat, and they got the data from that. And the idea was to see, if when the thermostat turns off, how fast does the place cool down? And that's a proxy for.
I've been involved with a study that did that.
Right.
Within schools, we had internal environment sensors, so you could see the time it took to gain or lose a degree in temperature.
Yeah.
To infer whether that was a well insulated space or not. In the absence of having that monitoring and running on electricity data, is there a way to kind of have another way? But that's kind of the interesting question for me. Is there a way to use that data that is available for everyone without the need for additional devices to then go, maybe we do need an additional device to.
Yes. I mean, we haven't looked at it. We have looked at some of the heating data. In the UK, we have these things called energy performance certificates for households. And there's a standard methodology which is an assessment of how much energy is this dwelling likely to use per year. And you get a kind of a rating from A to E or something like that. And there's a standard methodology for estimating that. And so we've done a little bit of work on like how good is that methodology. And it turns out there are assumptions in it that are completely wrong. But it might be that the actual number they come up with is okay, even though their assumptions are completely wrong. And we haven't got that far, we just got as far as determining our assumptions aren't good.
So I was wondering about the applications of the disaggregation work. You talked about one sort of particular application. Do you know of, or are you thinking about other applications
of disaggregation? We're not really going any further with that. And there are quite, you probably know there are companies out there marketing disaggregation as a and trying to sell like disaggregation service to like utility companies. And we did engage with Scottish Power, which is one of the big utility companies in Scotland, well, across the UK actually, about this. And it turned out that they were mostly interested in providing disaggregated sort of information back to the consumers as a marketing tool. So, they're doing more for their consumers than anybody else. They weren't interested at all in how much effect it actually has on energy use. Yeah. So no, we haven't done it. I mean, I think the future of disaggregation work. I mean, at the moment we're in the CARE project. We're trying to apply these disaggregation methods, and it turns out none of our households had solar panels or heat pumps, because they were still relatively uncommon in the UK in 2013, and they're not fantastically common even now. But the housing association that we're working with, it wants to put solar panels on everybody's houses, and the way that if you can't extract the solar input into the system, then it completely messes up your disaggregation. So that depends on, what is the smart meter measuring if you've got solar. So it's sort of a moving target.
Helen, do you have any questions you want to ask?
Can you, not specifically, I found it all fascinating, and I'm rather envious of the smart meters that you obviously have in the UK compared to the kind that are rolled out here. Can you hear me?
Yes, yeah, we can hear you. What are the smart meters?
Well, we don't get the 10 seconds.
Ah.
Well, there's the 10-second data, and there's also the fact that it sounds like the household inhabitants have an interface to look at their data through, rather than it being entirely for the benefit of the company as it is here.
Yeah, well, that's right. So everybody gets an in-home display, and it shows, it shows some information.
Here we have no in-home displays.
Right, and there's just 30-minute data, or?
I think some of them have 15-minute data, but it varies depending on which metering company installed the meter, which varies depending on which company the household was with when the smart meter got rolled out in that area. It's very hit and miss.
Yeah, it's interesting. So when we started talking to smart meter companies and sort of working on this, we were told that the smart meters in the UK, and it might well be the same here, are actually capable of producing data at much faster rate than even 10 seconds.
I was going to ask what you might know about their maximum rate.
Well, I think it's in the kilohertz.
Yeah, which is what I would have thought.
The reason they don't do that is because that would be an enormous amount of data, And in the UK, they're shipping the 30-minute data over the mobile phone network. And they have in the gas meter, they've got a huge capacitor, which is the energy source for, I don't know, 5 years or something. That's going to be 5 years of energy to, so, you know, energy is a real issue for the gas meter because it's not, the electricity meter is fine because it's connected to the electricity. The gas meter has to talk to the electricity meter so that it can get its data out. So yeah, the meters can go a lot faster, and we're in the next version of the CARE project, we have a partner called Census, which is an innovation centre around in Scotland around sensors, and they're looking at trying to get some of this kilohertz data out. And they say it's just a matter of new firmware in the meter, so it doesn't cost any, you know, it's just download and update to the firmware, which can be done over the air. You know, you don't have to send somebody around. So you know, it's sort of in principle doable, but there are probably incredible bureaucratic hurdles. The advantage of kilohertz data, from what I understand from the literature I've read, is that you can pick up on the harmonics, which are different for different kind of devices. So you could probably detect a TV because it has particular kinds of harmonics versus LED lighting or, you know, whatever it is. So there might be some advantage to that if it could be gotten. The reason, as I said, I think the reason that they mandated 10-second in the UK was they were trying to sell sort of politically into the whole concept of the smart meter program. And so they felt the need to kind of sell it to people. So you're not required to have a smart meter. Are you required to have smart meters here? Or can you say, no, I don't want one?
You can say no.
You can say no, yeah. So they didn't want people saying no. So they wanted to provide some benefit. I mean, like, why would you say yes here? Is it just because you get?
I don't think you say yes. I think here the companies install them unless you specifically say no. It's an opt-off, basically.
But we've had very high levels of uptake.
Right.
There's not the resistance that I think you've faced in the UK.
It's up to 90% or something.
Right. Well, people in the UK are very untrusting of their government.
And there's been quite a bit of negative press with
with
respect to the
reason.
smart meter rollout as well.
Yeah.
That's been quite in the media quite a lot. And
Yeah.
As soon as things started to go wrong, then obviously the media over there seems to love latching onto that type of thing, and making a bigger deal out of it because there's nothing else to do. So.
Yeah, absolutely. Yeah, and I mean, it's true that, so the half-hourly data that goes to the half-hour, it's interesting in the UK, the half-hour, unlike I think some European countries, I don't know how it is here, the half-hourly data sits on the meter. It doesn't go, and then if you want access to that data, like the billing, the energy supply company wants access to their data, they have to get permission. So the energy supply company sort of automatically has permission to extract that half-hourly data. But if we want it, there's a project that we're part of at UCL called the Smart Energy Research Lab, and that is getting smart meter data from like 10,000 different homes across the UK and doing lots of studies on it. But it costs about £1 million to get to go through the process and the technology of accessing this data on the meter. And when you access it, you pull it off the meter and put it in your database. There isn't a central database anywhere that has this. Because people were very, you know, it's quite personal and it's a security risk. I mean, you can tell when people are on holiday. And, you know, you can tell if somebody who says they're, you know, they're not working, actually looks like they are working. No. So there are all sorts of reasons why you don't want, you know, your energy data, especially at 10, even at a half-hour level, you know, getting out.
Okay,
Great. So I think we will just thank you for the talk, and
Yeah, you're welcome.
there's a few of us who are going to stay around and continue chatting with you.
Yeah.
And you're all welcome to stay. And so we probably didn't sort of introduce that we've got facilities people and academics in the room.
Right. Yeah, well, I'm very curious to know, what sort of work in these areas is going on here in Otago and more generally in New Zealand.
That's what our plan is, to tell you a little bit more about that.
Great.
So, yeah, so well, thank you for that. Helen, were you hoping to stay with us for this next session?
I think that would probably end up being quite awkward, but I'd just